Welcome to Mathematical Analysis. Today, we are diving into operators and divided differences. Imagine tracking a car's speed, but your camera only takes pictures at random, irregular intervals. How do you calculate the rate of change when the gaps between your data points are constantly shifting? This is the exact problem divided differences solve. They are the mathematical foundation for understanding unevenly spaced data, allowing us to build continuous curves from scattered points. Let us begin our journey into this fascinating topic. Now that we understand the premise, let us look at why this concept matters. In the real world, data is rarely perfectly spaced. Weather stations miss readings, and stock markets have irregular trading times. If we want to measure how fast something is changing across these random intervals, standard slope formulas fall short. A divided difference is a customized mathematical operator. It calculates the rate of change by adjusting itself based on the exact physical distance between each specific pair of points. This ensures our calculations remain accurate no matter how scattered our measurements might be. To make this idea concrete, let us look at the mathematical definition. The first divided difference is essentially the slope of a straight line connecting two points. On the left, the square brackets denote the divided difference operator for the inputs x0 and x1. In the numerator, we have the difference in the function's output values. In the denominator, we have the physical gap between the two input points. If the gap between the input points increases, the denominator grows larger, spreading the change over a wider interval. This gives us the exact average rate of change between those two specific data points. Before we move on to higher orders, let us see this with a concrete visual. Here we see a continuous curve with three unevenly spaced data points. The straight lines connecting these points are called secant lines. The steepness or slope of each secant line represents the first divided difference for that specific pair of points. Notice how the horizontal gaps between x0, x1 and x2 are not equal. By dividing the vertical change by these specific horizontal gaps, the divided difference accurately captures the average rate of change across each unique interval. Now that we have visualized the first divided difference, let us step up to the second divided difference. This involves three data points. Conceptually, this measures how the rate of change itself is changing, which relates to the curvature of the graph. The numerator subtracts the first divided difference of the first pair of points from the first divided difference of the second pair. The denominator is the total span from the very first input point to the very last input point in the set. If this value is positive, our slope is getting steeper. If negative, it is getting flatter as we move across the data. Having defined the operators, we now encounter a fascinating and highly useful feature called the symmetry property. This property states that the value of a divided difference does not depend on the order in which the points are listed. Whether you calculate the difference from point A to point B or from point B to point A, the final numerical result is exactly the same. This makes calculations much more flexible, as we do not need to worry about sorting our data points before analyzing them. Let us look at the mathematical statement of this property. This simple equation represents the symmetry property for the first divided difference. The left side is our standard divided difference from x0 to x1. The right side evaluates the points in reverse order from x1 to x0. The property guarantees these two are perfectly equal. Furthermore, this holds true for divided differences of any order. A third-order difference is identical regardless of how its 4 points are shuffled. Now that we have stated this identity, let us prove exactly why the order of the points does not matter. Let us prove this mathematically for the first divided difference. We start with the standard definition. The numerator represents the total change in the function's output values, and the denominator represents the total change in the input values. To show symmetry, we need to reverse the order of these terms. We do this by factoring out a -1 from both the numerator and the denominator. By pulling out the negative sign, we mathematically reverse the order of the terms inside the parentheses. This algebraic manipulation does not change the actual value of the fraction, but it sets us up for the final result. Continuing from our previous step, we now have negative signs in both the top and bottom of the fraction. These negative signs cancel each other out completely. Once removed, we are left with a new, clean expression. Notice that this resulting expression is exactly the formula for the divided difference if we had started our calculation with the second point instead of the first. The mathematics naturally reorganizes itself to show the reverse perspective. We have successfully proven that the first divided difference is symmetric, confirming that the order of points does not affect the result. So, we have proven that symmetry holds. This brings us to a beautiful and deep connection between divided differences and the derivatives you learn in basic calculus. A derivative measures the exact instantaneous rate of change at a single point. A divided difference measures the average rate of change over an interval. If we take the points in a divided difference and squeeze them closer and closer together until they merge into a single point, the divided difference transforms directly into a derivative. This bridges the gap between discrete data points and continuous smooth curves. This powerful theorem formalizes that connection. The left side is the nth divided difference calculated over a set of points. The right side represents the nth derivative of the function, evaluated at some unknown point eta that lies somewhere between the smallest and largest input values. The denominator is n factorial. This formula tells us that a divided difference is essentially an approximation of a derivative, scaled down by a factorial. If the function is a polynomial of degree n, its nth derivative is a constant, meaning the nth divided difference will also be a constant everywhere. This relationship to derivatives leads us to the entire reason we calculate these divided differences in the first place: interpolation. Interpolation means constructing a continuous curve that passes exactly through a set of known, discrete points. The divided differences act as the building blocks or coefficients for a specific polynomial that connects these dots. By calculating these differences, we can build a mathematical bridge between scattered data points and predict the value of the function at any new point between our known data. Let us look at the formula that makes this possible. This is Newton's divided difference interpolation polynomial. The left side is the polynomial of degree n that we are trying to construct. The variable x is the new input value where we want to estimate the function. The terms with square brackets are the 0th, first, and second divided differences. The terms in parentheses are weight factors that turn on and off as x moves past the known data points. In plain English, this formula starts with a base value, adds a linear correction based on the first slope, and continues adding finer curved adjustments for every point we have. Before we build the full polynomial, let us see this with a concrete example of calculating the differences. Suppose we are tracking an object. At time 1, the position is 3. At time 3, the position is 11. At time 6, the position is 38. We want to find the first and second divided differences. We start by calculating the first divided difference between the first 2 points. The change in position is 11 minus 3 and the change in time is 3 minus 1. Dividing 8 by 2 gives us 4. The object is moving at a steady pace of 4 units during this first window. Continuing with our data, we next calculate the first divided difference for the second pair of points. The position changes from 11 to 38 and the time changes from 3 to 6. Dividing 27 by 3 gives a rate of change of 9. The slope has increased, indicating acceleration. Finally, we calculate the second divided difference. The numerator is the difference between our two first divided differences, 9 minus 4. The denominator is the total time gap from the first point to the last point, 6 minus 1. Dividing 5 by 5 yields a final result of 1. This represents the constant acceleration over the entire period. Now that we have calculated the divided differences for our 3 points, let us use them to construct Newton's interpolation polynomial. We will use the exact same data points. We already know our divided differences are 3, 4, and 1. Our goal is to write the general quadratic equation that passes perfectly through all 3 points. We take the explicit formula for Newton's polynomial of degree 2. We substitute our known input values, which are 1 and 3, and our previously calculated divided differences into this template. This equation is already a valid representation of the curve, but we need to expand it. Continuing from our substituted equation, we begin the simplification process by expanding the terms algebraically. We distribute the 4 into the first set of parentheses. Then we multiply out the two binomials to get a quadratic expression. This breaks the formula down into individual manageable pieces. By combining all the like terms, the linear variable terms cancel out completely. The constant numbers simplify down to a final value of 2. The final simplified polynomial is just x squared plus 2. If you plug our original input values into this simple equation, you will get exactly the original output values, proving our curve is correct. We have covered a lot of ground today. Let us reinforce the most important ideas. First, the divided difference operator is a flexible tool for calculating rates of change across unevenly spaced data points, adjusting for the exact gaps between measurements. Second, these differences possess a symmetry property and share a deep mathematical connection to derivatives, acting as discrete approximations of continuous rates of change. Finally, they form the backbone of Newton's interpolation formula, allowing us to construct continuous, predictable curves from scattered discrete measurements. You now have a powerful method for analyzing complex, irregular data in the real world.